Welcome to Joffier Whispers. My name is Nairi. I want to talk to you today about something close to my heart as a musician and composer, which is sound. But not just sound as a phenomenon, sound as a potential healing tool. And the question of the pitch of sound, you've probably heard so many comments online about the difference between setting music at a standard pitch of A at 440 as opposed to A at 432. And what prompted me to do this video was hearing somebody online or reading somebody online saying that a friend had discovered that the universe vibrates in the pitch of F sharp major, which of course is silly nonsense. The universe doesn't know pitch, it makes its own rules. But it got me thinking about how few people understand the implications of the difference between those two pitches and why we have A440. So when I was young, we were told, and I believe it, that A440 was chosen as a standard because orchestras sounded brighter at A440, and certainly brass instruments in particular do sound better at that higher pitch. But of course, before about the 1950s, when A440 was introduced, there were no standards. And what people don't realise is that 432 was not a standard either. The pitch of your instrument is relative to many factors. It could be the type of material your instrument was made of, the room you're in. If you take a piano from a warm room and move it, if you can be bothered, into a cool room, you'll find that the pitch changes dramatically. In the time of Beethoven and Mozart, they would have played at different pitches, at different standard pitches, depending on where they were and which instruments they were using. So to say, some people seem to think there's some kind of conspiracy about A440. I personally don't believe there is, and I have no problem listening to classical music. I've loved it all my life, and it's always been at that particular standard. But if we come to discussing sound healing, perhaps that's a different matter. Perhaps for sound healing, this is important. But what also is important to me is that people really understand what these things are about, and not just talk wildly about how the universe is made and it all comes down to the key of F sharp and silly things like that. So let's have a look at where all this has come from, if you're interested to go on to come on this journey with me, because it is really interesting. And to do so, we actually need to go way back between 4,000 and 8,000 years to ancient Mesopotamia, to Sumeria, where they used a very different counting system to what we use now. We use base 10, and you can imagine that probably base 10 is based on the fact that we have 10 fingers and it's easy to count. You count up to 10, you put a stroke in the sand and a 0 as a placeholder, and then you do another 10 and so on. But in ancient Sumeria, they used a system we refer to as 1260. And this is how it works. If I hold up my hand, you can see, of course, that we have three joints, three sections on each finger. So in those days, they would have used the 4 fingers to count on, not as whole fingers, but use the sections of the fingers. So we get 1, or we start over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the number 12. And then we go over to the right hand and say 1 lot of 12. And then we do it again, 2 lots of 12, up to 5. What does 5 lots of 12 give you? 60. I want you to think about that. How much of those early concepts remains with us to this day? In terms of 60, we have 60 seconds in a minute, 60 minutes in an hour. We have a nautical mile is 1/60th of a degree of the circumference of the surface of the Earth, which is 360 degrees. 60 comes up in many different ways, or divisions of 12. We have 12 hours in the day, we have 12 signs in the zodiac, we have 12 eggs is a dozen, 12 inches in a foot, 12 ounces in a pound. We still use a lot of those measurements that come back from all that way back in the past. And here are some other interesting things about the number 60 and the number 12. And by the way, Buckminster Fuller believed that the base 60 in his mind was somehow the key to the universe. A lot of people think this. But here's a couple of other little statistics that might interest you. The Earth doesn't just rotate on its own axis and rotate around the sun. It also has a wobble, and the time span of that wobble is 25,920 years, which means it forms a sort of conical aspect to the centre of the Earth. If you divide that by 60, you get the number 432. Isn't that interesting? If you multiply 432 by itself, square 432, you get the speed of light. The sun is approximately 864,000 miles across. If you divide it by 2, you get 432. The moon is approximately the quarter of the diameter of the sun, again divisible into 432. So those three numbers come up all the time when you're looking at relative relationships. And by the way, 432, if you multiply 4 by 3, you get 12, which is the numbers of hours in the day, and the number of hours in the night, you multiply it by 2 again, and you get 24, which of course is the 24-hour cycle. Again, you get divisions of 12. What else is there to say about 12? To me, 12 makes sense as a counting system. It totally does. Why should we use base 10? Base 10 can only be divided by itself and 5. Base 12 can be divided by itself. Oh, and 1, of course. Base 12 can be divided by itself, by 2, by 3, by 4, by 6, and then it can't be divided by 8, but if you halve 8 and multiply it by 3, you get 12, and if you take a third of 9, which is 3, multiply by that by 4, and you get 12. So 12 is actually a whole number. It's a number that's about ratios and relative values, as opposed to the decimal system, which is an artificial construct and which mostly results in calculations to the decimal point. They're not whole calculations. So how is this relevant to our conversation about A432 in the end? Well, let's go from ancient Sumeria to something that's called sonic geometry. If you have a look at these geometric shapes, you probably know from high school geometry that a triangle of any sort, but in this case an isosceles or equal-sided triangle, is regarded as containing 180 degrees. Divide by 6 and you get 3, so it's a multiple of 60 and 12. A square gives you, if you add 180 to itself, you get 360 degrees. If you get a pentagon, that is, you add one more side, you get 520 degrees. If you add another side and get a hexagon, you get 900 degrees. And so you get the idea, it goes on. All of those divisible by 12 and divisible by 60. They create whole numbers, not decimal points, whole numbers, which can be reduced and multiplied forever without losing their value. Whereas when you divide and multiply with decimals, especially when there are decimal points, it becomes so complex, it's very unwieldy. But back to the degrees in the triangle. Now, I'm sorry I couldn't find a more revealing graph, but here's an image of the geometric shapes. As I said, a triangle is regarded as containing 180 degrees. Now, if you take an open string and vibrate it at 180 hertz, not degrees, but hertz, vibrations per second, you will get the pitch that we call F sharp. And the only reason that pitch is at F sharp is because we tune our instruments to A440. If we didn't tune to A440, it would have a different name. So the name's not important. The name is only useful so we can make comparisons. So don't get lost in that. If we then take the square, and we've already got 180 degrees in the triangle, if we add another 180 degrees, we get 360 degrees, which is the square. And again, if you vibrate a string or make a vibration of 360 hertz, you get another F sharp in pitch. When you go to the next figure, the 5-sided pentagon, at 720, you get a pitch that we call C sharp. And so it goes on, all right? And I'm going to explain to you this with a diagram shortly, but I just want to point it out with you looking at the various sided figures. Now, this diagram goes up to 12. Just a point of interest, when you get to 12, it's beginning to look more like a circle than a geometric shape, than any other geometric shape. So here's a question. How many sides do you have to add for it to become a complete circle? And if you know any maths at all, or even if you have some intuition about it, you'll realize never. There are an infinite number of sides to the circle. And that word infinite, to me, has a key to how everything functions, the whole universe, our sound, everything. So let's look at this diagram of a piano keyboard. And this is a keyboard, an electric keyboard. It wouldn't be an acoustic piano because the numbers wouldn't be so precise on an acoustic piano. They would be more approximate. There are a few things to note about this. Firstly, you note that all the numbers, if I go up to E here, you'll see the number is 82.4 hertz. If we go over here, 116.5. Here we even have 207.7 hertz. Nature isn't that precise. We don't have decimal points in nature, but this is how they fall if you tune it electronically. If we go up to the very top, this A here, and you'll see this A vibrates, or it's the bottom on the piano, actually. It's the left-hand side. These are the lowest notes. And if we go down, we actually go higher and higher in pitch. So let's go back up to the top with the lowest note, A, that they have on this chart, and it vibrates at 55 hertz. If we double that, 110 to 110, and go down here and we find 110 hertz, we find that that is also A. If we go down further, double that, go to 210 hertz, here we go, that's also A. And if we double that, we get 440, the infamous A440. If we go down here, we don't actually have it on this chart, but you can see we've got to 392. And if we go down to A, that will indeed be A440. And that pitch is less than an octave away from the center of a piano. That's about where it lies in the sound, the scheme of things, sound-wise. A couple of things to point out. Firstly, all of those numbers are only all divisible by 1 and 10. None of them are evenly divisible by any other consistent number, only by 10. And if you think back to what I was saying about sonic geometry, you will realize that that is significant, that there's no common divisor. If we go over here, on the right side, bit more than halfway down. See this number 185 hertz. And we go across here and we have an F sharp. So F sharp on this keyboard vibrates at 185 hertz. I want you to remember that number, but I will remind you in a minute why it's significant. F sharp, 185 hertz. If we now go to the other image I want to show you, which is this one. Now here we have two chords. We'll call them chords, but they're actually more than just chords. What they are showing is what we call, for non-musicians, what we call overtones or harmonics. What does that mean? Well, if you sit at a piano keyboard and an acoustic piano, and you take off the dampers so all the strings are free to vibrate, and you press quite loudly on this particular pitch C, you will find that not all the strings vibrate, but some of the strings will vibrate sympathetically. The first string that vibrates sympathetically is 1 octave above, 8 notes above, and that gives you another pitch C. If we go a fifth above that, that string on G will vibrate. If we go up to C, that will vibrate. So we now have C vibrating in sympathy, C vibrating in sympathy, and we also have G vibrating as well. Now this C is also the same as this one. You can see they're exactly the same note, but one is bass clef, one is treble clef. So we've already had an octave and a fifth and a fourth. If we go from this C up to the next sympathetic pitch, we get the note E. Now that's a distance of 4 semitones. If we go to the next sympathetic vibration, it is 3 semitones. So we've got C, and then we've got 4 semitones to E and 3 semitones to G. And if we pop up here, we've got the same 3 notes, but an octave higher, C, E, G. So C to E, 4 semitones, E to G, 3 semitones. And then we have the next overtone is two semitones away. It's the pitch A. And then the next one semitone away, the B flat, B flat. And if you had any more strings on the piano that could tune to even finer distances, what's the word I want? Doesn't matter. If you had quarter tones on the piano, you would find the next sympathetic vibration after B flat is B flat sharpened by a quarter tone. And we can't do that on a piano. You can do it on other instruments. You can do it on brass and woodwinds, but not on a piano because the pitches are fixed and the maximum distance is a semitone. But so you see, there's a pattern of notes here. Overtones, they occur naturally. And it doesn't matter which note on the piano you press, if all the strings are loose, any note you press will have a series of overtones in the same pattern, exactly the same pattern, but beginning at a different pitch, which of course raises all sorts of issues when it comes to performing music and why some combinations sound better than others, but that's not the point of our conversation today. Now, if we take that pattern and instead of using C as the fundamental note, we're going to come over here to the right and you'll see I've used F sharp as the fundamental note, vibrating at 180 hertz. And if you remember from what I've just said about acoustic geometry, this is a naturally occurring note. It occurs just in nature. Do you remember on the keyboard, I said, please note the F sharp on a keyboard is adjusted to 185 hertz. In other words, slightly higher than 180 hertz. So this is a lower pitch than the F sharp on the piano. If you look at the pattern, you'll see it's identical to this one you see on the left. the top set of notes on the left, I'm circling, you'll see the pattern over to the right in this key is also the same pattern. Now, I just need to point out one thing, and this is more relevant to people who've studied music and know about acoustics. Please note, I've put ottava up the top, and there's a technical reason for that, and it needs to be clear. Ottava means, 8VA means ottava, which means that you play this pattern of notes a whole octave higher than they are written here. And of course, that's just to make it easier for a pianist to play something. If you had all the notes written way up here off the stave, they'd find it difficult to read. And that's why I put it here for you, so you can see the relationships. What does that mean? It means that actually this note, F sharp at 180, should really be up an octave higher. This is F180. Now, that's just a technical explanation, and you can forget it for now because we're looking at the relationships. We start at 180. We get the octave higher at 360. By we're adding 180 to itself, we get 360. We add 180, we get the first overtone. We add another 180 and we get 720, which is the next overtone. Can you see the pattern is exactly the same? But look at these numbers. What's the difference between these numbers and the numbers on an electronic keyboard? Well, they're all whole numbers for a start. They're all divisible by 10 too. But they're also divisible by 5. They're divisible by 4. They're divisible by 12. They're divisible by 60. In other words, there are many, all of the notes, all of the relative pitches are divisible, equally divisible. So it's a natural pattern. So what about the famous number 432 or infamous number 432? Well, that relates to all this, as we said earlier. And here you can see it visually. We come down the bottom to F sharp. We have F sharp an octave higher. We have F sharp an octave higher and an octave higher again. They're all sounding. Then we have the perfect fifth, which is C sharp. Here it is, and here it is again. And then we get back to this octave, and then we get to this major third, which is A sharp. Now, bearing in mind that technically this A sharp is up here, up the top. So this is just a way of you being able to see the relationships. This pitch would actually not be 900 in reality. It's 450. And what's the number we're looking at? 432. It's in the ballpark of 432. If you come down a semitone from A sharp, you will get an A, which of course falls at 432. It's lower than 450. So there is that F sharp, that A, that number A, 432, is right here on the piano. And where it falls, if you're sitting at a piano, is just within an octave to the right of where you're sitting. It's almost in the middle of the piano. That's the pitch we're talking about. I hope that explanation made sense. It's quite a complex idea, and yet it's quite complex to talk about, but in concept, it's really not that complicated. It's quite simple.
One other little diagram I want to show you. I'm sure you've seen it online. It's coming up all the time now. And it's simply the sound vibrations of, I presume, a metal plate with sand on it. One is being vibrated at the rate of A440, 440 hertz, and the other one at 432. And you'll see that the one at 440 looks pretty rough, whereas the one at 432 creates a regular pattern. Now that's only two-dimensional, and the universe isn't two-dimensional. It's at least three-dimensional, if not more. But try and imagine that shape in a circular shape and see, can you understand how that can be a key to how all matter formulates? And here's another thought. If sound is capable of getting particles to coalesce in that way, is it possible that if sound is powerful enough, it can get those particles to coalesce
in such a way that it creates such solid matter that it's impenetrable. So is the key to the universe really about sound? You know, Pythagoras believed that was the answer. A lot of metaphysicists believe that's the answer. Leonardo da Vinci, I think it was, talked about music of the spheres. Pythagoras, I think it was Pythagoras, even worked out that the ratios between all of the planets are the same as the ratios between the overtones of a single note. So that's, you know, these patterns are, it's not just one or two. There's too many to be coincidence. There's obviously a correlation between all of them. And so that's just food for thought. I certainly personally think that in terms of sound healing, it's very clear that to harmonise the body, we need to create harmonious sounds, and that doesn't really happen with an orchestra, at least, and with ensembles. If you play a solo instrument where you can alter the pitch, you probably tend to shift more into that range. I don't know. But anyway, that's food for thought and something for you to think about. Let me just remind you that I do have a website at narij.com where you can listen to a little bit of my music and look at my paintings, find out a bit about me. And until next time, stay well, stay blessed.